Hello again, Mr. Munyon here with activity 14-3, perpendicular bisectors and angle bisectors. So our goal here in activity 14-3 is determine the points of concurrency of the perpendicular bisectors and the angle bisectors. So same thing we've been doing with the other points of concurrency. We've got a couple new vocabulary words. Luckily, we should actually already be pretty familiar with what these mean. Perpendicular bisector is exactly what it sounds like. If you take a side of a triangle or a segment, you need to bisect it, so find the middle point and be perpendicular. So we're going to create segments that are perpendicular bisectors. Same thing with angles. The angles on a triangle, we need to bisect the angles so that we create two congruent angles on each of the triangles. All right. So the third part of the poem that we were dealing with in 14:1 and 2 says, each locked in chest where they will stay until the time someone finds a way to open each lock with a combination using digits of the coordinates of each location. So the coordinates of each location refers to the coordinates of the orthocenter and the centroid that we found from the previous lessons. If the combination consists of three numbers or three digits, list some possible combinations for the lock on the second chest. So the points that we came up with were 12, 12, and 16, 8. So I guess the only numbers we have are 8, 12, and 16. So some combination of those three numbers. So like 8, 12, 16, 16, 12, 8, 16, 8, 12. Just any possible combination of those numbers. All right. So Al, Jeff, and Cal found the treasure by locating the point of concurrency of the altitudes of the triangle called the orthocenter. We did that one. And the point of concurrency of the medians called the centroid. Just did that in 14-2. Cal tells Al and Jeff to learn about two more types of points of concurrency called the circumcenter and incenter. Before they design the nature preserve, they start by locating the coordinates of the circumcenter. So to create a circumcenter, that's where the points of concurrency of the perpendicular bisectors meet. So we need to find the perpendicular bisectors. Al took an algebraic approach similar to the manner in which he found the orthocenter. He calculated to be at 18.6. So at 18.6 is where he calculated this to be. Jeff decided to carefully sketch the perpendicular bisectors of each side of the triangle. Let's go ahead and draw those on here now. So I'm going to zoom in a little bit so we can find the perpendicular bisectors. So the first step of a perpendicular bisector is going to be to find the midpoint. So you have to bisect each side, and we did that earlier when we did the medians, so we already know where the midpoints are going to be at. From there, we just need a perpendicular line. So I went ahead and added the slopes that we got from earlier as well, so that we could do the opposite reciprocal slopes from that midpoint. So this is probably the easiest one here. From this midpoint, using a perpendicular slope would just be a vertical line. So I know this one's going to be like that. From here, I need a line that goes through this midpoint and is perpendicular to -1, so it should have a slope of +1. So it's going to go like this, having a slope of +1. That need to go too much farther, and I've already found the point of intersection. This last one should. Let's just make sure. If I start this point and use an opposite reciprocal slope, so the opposite reciprocal of 2/1 is -1/2. So rise of -1, run of 2. Looks like we do get that point there. All right, so we have sketched our perpendicular bisectors and found the circumcenter. All right, so now does our drawing verify that Al is correct? Yeah, it looks like we did get that point. 18.6 is what we came up with there. So 18.6 is the circumcenter. Now it says there's a special property, and we didn't label that point Q yet. I guess I could label that Q right there. It says find the distance from the circumcenter to each of the original vertices. So we could do this using the distance formula. So if I wanted to find the distance between 2 points like 0, 0 and 18.6, I could use the distance formula. So the change in x from 0, 0 to 18 would be 18. The change in y goes from 0 to 6, so 6 squared. And let's see what we get. All right, so 18 squared is 324 plus 36, and we get 360. Square root of 360 is approximately, oops, there we go, 18.9. I don't know exactly what it is, about 18.9, somewhere around there. So we could say square root of 360 is that distance. And or we could calculate the approximate value with our calculator, or we could use some software to figure this out as well. So I'm going to go ahead and hop on over to GeoGebra. And here I have set up the perpendicular bisectors, and they meet at the circumcenter here. Notice this is exactly in the middle, perpendicular. This is exactly in the middle, perpendicular. Same thing here. So I'm going to find the distance here between each one of these and the circumcenter. So between the circumcenter and A, that distance, between the circumcenter and B, that distance, and the distance between the circumcenter and C. Well, I guess it was labeled differently on ours, but notice all of these are exactly the same. We get 18.97, 18.97 on every single one of these. So the distance from the circumcenter to a point our vertex is always going to be the exact same, or at least on this example it happens to be the exact same, maybe all. So all of these should be square root of 360, or about 18.97. All right, so now that we know the distances are the same, it says the distances suggest that the circumcenter of a triangle is equidistant from the three vertices of a triangle. Write a convincing argument that this special property applies to all triangles. So hopefully when you first learned about perpendicular bisectors, something you learned was that any point on a perpendicular bisector is going to be an equal distance away from the endpoints of that segment. So for example, look at this perpendicular bisector right here. Any point on this perpendicular bisector, like this point way down here, is going to be the exact same distance away from points A and C. Any point, notice here, same distance away from A and C. So if I have a different perpendicular bisector, like this one here, any point on this line is going to be the same distance away from B and A. So when I find a point that's on both lines, because it's on this perpendicular bisector, it's the same distance away from A and C. Because it's on this perpendicular bisector here, I know it's going to be the same distance away from A and B. So this point, because it's on two different perpendicular bisectors, is the same distance away from B, A, and C. It's the same distance away from all three vertices. And if I was to pick some points and move them around, notice those distances, no matter where I put this, the distance from the centroid F to a vertex, all of them are going to stay exactly the same distance. No matter where I move these other vertices, the distance from the circumcenter to the any vertex is always going to be the exact same. So where was this one at? All right. Going back to ours, here is a nice explanation of what I just said. Any point on the perpendicular bisector, blah, blah, blah. You can pause here and copy this down if you want to. That's just a verbal explanation or written explanation of what I just explained verbally. All right, so the next thing says sketch the circumscribed circle on the grid in item 2. So what this is asking us to do is sketch a circle circumscribed, so the triangle is touching the circle at all three of the vertices. So if I scroll down here to draw a circle with the center and a point on the circle, so select the center of the circle, notice when I go out to here, because the distance to all the vertices is the same, that's like drawing a radius from the circumcenter to the vertex, and the radius is the same to all three of these. That's why it's called a circumcenter, because it's circumscribed inside of the triangle is circumscribed inside of the circle, with the center of the circle being the circumcenter. So conveniently, when you do this, we actually are able to draw a circle that goes through all 3 points. It's an easy way to check your work for that. All right, kind of interesting. Back to our problem. We just did this one on GeoGebra. All right. Cal located the incenter. So new problem here. And he estimated that the coordinates of the incenter are at approximately 14.4, blah, 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 8.9. So the incenter, don't know if it has the definition on here. Yeah, the incenter is the point of concurrency of 3 angle bisectors. So I know it's not drawn on your PDFs, but I went ahead and drew the angle bisectors here and found out they were did intersect at about 14.4 and 8.9. So 10, 12, 14.4, 8.9 does look like they intersect there. I've got all my angle bisectors drawn. On the grid below, carefully draw, we just did that, label the point of concurrency I, so that point would be point I. Does your drawing support Cal's results? Yeah, it does look like that is the point of concurrency. So here it wants us to eventually do a bunch of other things and figure out the distances or the special property that an incenter has. It says sketch the inscribed circle and notice what happens there. So on a different page, I have created an angle bisector here. And notice these are the coordinates that we were using before. On GeoGebra, you have the option of doing angle bisectors by just picking any 2 pieces or any 2 legs of an angle here. And I guess we could do this one more here. And they do intersect at about 14.4, and 8.9 is exactly where they look like they intersect at. So let me put a point there just to be sure. And then check what are the coordinates. Okay. It does look exactly, point D there does look 14.44, 8.9, whatever we got there is the exact same as from this one. The problem that we were trying to do, we weren't trying to find this point. They already calculated for us, but it said draw an inscribed circle. So instead of drawing the triangle inscribed within the circle, we're going to be drawing a circle inscribed within the triangle. So let's draw a circle here. Make this the center. And notice it kind of snaps into place there. This is touching all 3 sides of the circle. This is an equidistance from, let me put some more points on there. I guess that might be the point where it was touching at. I don't think that would be the point. Should be a little bit farther over here. Well, I'll get rid of that one in just a second. In any case, because once again, the same property is true that we mentioned before. Because this is a circle, any radius on this circle is going to be the same distance. So from point D, the incenter of this circle, to any point on the circle is going to be the exact same distance. So point E, point F, and not quite point G, because point G should be down here somewhere. But in any case, should be the exact same distance there. So an incenter is the same distance from all 3 sides. A circumcenter is the same distance from all 3 vertices. So perpendicular bisectors find a point that's the same distance from the vertices. Angle bisectors get you an incenter that's the same distance from all 3 sides. Now, knowing which of those goes together is kind of hard to do. So we're going to have a little moniker or acronym you guys can use to help you remember which points of concurrency go with which special segments and triangles and what property they have. All right. So drawing that one, we did figure out that the properties show that it's the same distance away from all 3 sides. So refer back to the description of the nature preserve. at the beginning of the activity on the map below, locate and label the three visitor centers, the power station, the campground. Explain why they chose these locations. So remember, the power station was at the circumcenter. Why did they do this? Well, the power station is an equal distance from all three vertices. So it's equal distance from all three visitor centers, and that makes sense because it needs to power all three visitor centers, so it's an equal distance away from all of them. The campground was found at the in-center. Why would you put the campground at the in-center? Well, we just learned that an in-center made up of angle bisectors is an equal distance from all three sides of a triangle. And so that's an equal distance from the three rivers. They could go to, well, the two rivers and the lake. From here, you could very easily go to this river, or this lake. And it's the shortest possible distance to any one of those by just drawing perpendicular lines to those. You can go straight here to this river, straight here to this river, or straight here to this lake. So each one of those is from the in-center. All right, let's check our understanding here. Pause here for a moment, try 12 and 13, and then we'll check our answers. All right, hopefully you've tried questions 12 and 13. Can the in-center of a triangle lie on the outside of a triangle? Let's check with GeoGebra. So the in-center, is it possible we could make this be on the outside of a triangle, point D? No, it looks like no matter where I put this, point D is always on the inside of this triangle. All right, so is it possible it could be on the outside of the triangle? No. And if you wanted to, you could mention something about it being in the center of a circle that's on the inside of a triangle, but we kind of already explained a little bit about that. For number 13, draw 3 sketches showing the circumcenter line inside, outside, and on the triangle. Make a conjecture about the location of the circumcenter based on the type of triangle. So let's look at our perpendicular bisector one that we had. So let's go back to this page and notice what type of triangle that we have and based on where F is. So if I was to move these vertices around, right now, what does this look like? Let's start here. Clearly an acute triangle. Right here, all of these are acute angle, maybe scaling. I don't know exactly. An acute scaling triangle. The circumcenter made up from these perpendicular bisectors is in. But if I move this around, at some point it does actually get outside of the circle. So at some point it's on the circle, and what do you guys notice? It looks like it's a right triangle. Let's move one of these other ones around and see if we can make a right triangle and see what happens. Yep. As soon as it's a right triangle, the circumcenter is on the circle. Interesting. Same thing here. Yep. Look at point F. As soon as it's a right triangle, we actually get it on the circle there. Okay, so far, acute triangles, it's in the circle. Right triangles, the circumcenter is on the circle, but what happens if we make it obtuse? So we make point A an obtuse angle outside of the circle. If I make point B an obtuse angle, if any one of the angles is obtuse, the circumcenter is going to be outside of the triangle. So notice here, if I make point C the obtuse angle, the circumcenter does move outside of the circle. Okay, so summarize, if you have an acute triangle, it's inside. If you have a right triangle, it's on. And if you have an obtuse triangle, it's outside. All of these sketches here are referring to the circumcenter. All right, let's look at some practice here. And let's use the properties we just learned about. Given triangle XYZ with circumcenter P, complete the following. So if PX equals 18, so PX equals 18, then PY, okay, so if this is a circumcenter, the property of a circumcenter is equal distance to each vertex. PY is going to be 18. That's easy. PZ is 18. That's about as easy as they get. What about if we have, the next one says WX is 12, then XY, what would that be? Well, if this is a circumcenter, it's made up of perpendicular bisectors. So this dashed line here is perpendicular. That means it's going to bisect. That has to be a perpendicular bisector to make this circumcenter. So this one is 12. So then the whole distance from X to Y would be 24. All right. What about the triangle below? We have triangle ABC. Question 16. D is the incenter here. So this is made up of angle bisectors. Complete the following. If DE is 3, so DE is 3. What is DF? Well, even though it doesn't look drawn to scale, I know that for an incenter, it's an equal distance to all three sides. So just by looking at it, you wouldn't guess, but because we know the properties of an incenter, it has to be equal distance from all three sides, and even this one right here, not drawn on there, but that one would also be 3. So DF also has to be 3. And if the measure, let's look at the next one here, number 17, measure of angle CAB equals 90, so CAB equals 90. And the measure of angle CBA equals 25. CBA equals 25. So this whole angle here is 25 degrees. What is the measure of angle ACB? Okay, we could do this just using triangle sum theorem. 180 total degrees in a triangle minus 90 minus 25 equals 65. And what is the measure of angle ACD? So ACD, cut that in half, we get 32.5. All right, so last two questions, we actually need to calculate the circumcenter. So I am going to do number 19, work through this one right now, and then I'll just put up the answer for 18 when I'm done. Actually, I'll put the answer for both of them up when I'm done here. All right, so let's check out. 19 had some coordinates listed at 2, 1. We had point X. At -5, -3, we had point Y. That one's labeled on there. And 0, 7, we had point Z. So to do perpendicular bisectors, the first step is find the midpoints. I've gone ahead and done that. If I average the X values of these 2 points here and here, I get a 1. If I average the ones here, 1 plus 7 is 8, 8 divided by 2 is 4, so at 1, 4, I do have a midpoint. From there, I would draw a perpendicular line, so I need the slope so that I could use an opposite reciprocal slope. Same thing, I'm going to use this other line over here between X and Z. Find the midpoint, find the slope. Average, I get -2.5 and 2 as my coordinate there. So I didn't write it down, but oh yeah, I did. -2.52. And I also need the slope. So rise of 2, run of 1 for all of those points on there. From there, I also would need the perpendicular slope to be able to plot this. So let's go ahead and use our point and our opposite reciprocal slopes to see exactly where our line starts ending up with. So from this point, this line here has a slope of -3. The opposite reciprocal would be positive 1/3. So 1/3 don't need to go that way. I'll go this way. All right, so this line right here has a slope of positive 1/3. And for this one, I need to do a perpendicular one from here. So if the original line had a slope of 2, the opposite reciprocal would be -1/2. So I'm going to use slopes of -1/2. So -1 and then 1, 2. +1 and -2. All right, so somewhere along here, is going to be, not exactly sure, might be here, might be here. Obviously, I didn't graph perfectly, but I think I might need to use equations to solve this one. So let's start with this part first. I have a point and a slope, so let's plug it into point slope form. There we go. So let's go ahead and plug in y minus y1 equals x minus x1 add 4 to both sides, distribute that 1/3, find a common denominator there. So we get 11/3. Okay. For our other equation, we can do the exact same thing. I have a point here at negative 2.52 and a slope of negative 1/2. So same thing I'm going to be doing here. My point was negative 2.52. My slope was negative 1/2. So let's plug that in. Add 2 to both sides. And I'll go ahead and distribute and add 2 on this one. So this could be, instead of 2.5, I'll just write it as 5/2, and that way I can distribute the 1/2 in there. So added 2 here, and I added 2 here at the end as well. Found a common denominator here. I rewrite 2 as 8/4, so I can add those together. So negative 5 plus 8 is positive 3/4. All right, so I now have the two equations I can set equal to each other. If y equals this and y equals this, I can substitute this in for y. So I'll take this value, substitute in here. All right, to make this a lot easier, I don't like these fractions, so I am going to multiply by 12. Why am I picking 12? Because that is the least common multiple of all of these, and that will get rid of all of the fractions at the same time. So let's go ahead and do that. All right, so let's multiply both sides by 12 then. Distribute in here, I get negative 6x. Distribute here, I get 9. Oops, that's supposed to be an equals up there. Distribute here, I get 4x. And then distribute here, I get 44. So subtract, I guess add 6x to both sides. We could do that. So add 6x here, cancels out, add 6x here. Subtract 44 from both sides. So minus 44 will give me negative 35 equals 10x. So divide by 10, x equals negative 3.5. All right, now that I know what x equals, or I could say negative 7/2. Now that I know what x equals, I should be able to plug it back into either one of these two equations here. And this one has a half in it. Might make it a little bit easier. We'll see what happens. See what we get for y. So I'm going to go ahead and plug it into this one here. See what we get for our y value. So y equals negative 1/2. X we just came up with was negative 7/2. So negative is positive 7/4 plus 3/4 equals 10/4, or divided by 2, I get 5/2, or about 2.5. Exactly 2.5. So my coordinate should be negative 3.5, positive 2.5. And this would be the circumcenter. All right. Let's go ahead and go back and put the answer for number, what was that, 18 as well. And for 18, should have been a pretty easy one. We get negative 1.5 and 10. Yeah, this one having this piece here and these made it real easy. These were conveniently on the axes. So drawing the perpendicular bisector should have been real. Two of them should have been real easy. The third one you don't need because you only need to find the intersection of two of them. You probably didn't even need to do any algebra for number 18. You could just draw a picture into it. All right, if you still are struggling with this, I would definitely recommend doing more than just the suggested homework practice for activity 14. There are tutoring times available. If you needed some more practice, please check out the live lessons tutoring that's available if you need some help with that. I will see you guys next time.